right, great. So it's 8 o'clock, so I'm just going to start us off. Thank you everyone for coming today and joining us first thing in your morning. My name is Jenna Annett. I work with the Community Energy Association. Just for a little bit of background on these webinars, I'd like to introduce you quickly to CEA and the Kootenay Clean Energy Transition Project. So CEA is a BC-based nonprofit. We've been working for over 25 years with local government and Indigenous communities across the province to reduce emissions, conserve energy, and help progress us to a low carbon and healthy future. Next slide, please, Rob. So the Kootenay Clean Energy Project, or KCET, Kootenay Clean Energy Transition Project, or KCET, is a project that was developed to address shifts that are happening in the energy efficiency, renewable energy, and home comfort space. So through KCET, we want to help Kootenay and boundary communities prepare for a more energy efficient and healthy future through training and capacity building for the building industry, community workshops to help increase knowledge and awareness, and pilot projects that we can test and scale up. So thanks to the generous support of the organizations you see listed at the bottom of this slide, we're offering this webinar series as part of that training and capacity building piece. Just the next slide there, Rob, please. Perfect. So I would like to begin today by acknowledging the Indigenous people from all of the diverse and beautiful places we are joining from. The land on which I'm currently joining you from is now known as Nelson, but for thousands of years was occupied by Indigenous populations and is the traditional territories of the Ktunaxa Nation, the Silks Nation, and the Snayaks Nation, and is home to the Métis and many diverse Indigenous persons. I just like to acknowledge with gratitude and respect that the joy I am privileged to experience daily in these mountains and waters is in thanks to their generations of stewardship. Just that next slide there, Rob. Great. So with so many of us on the call, I'd just like to take a minute right away to quickly talk about some housekeeping items. If you have questions as we go through, please put them in the chat for the end of the session when we have time for a facilitated discussion, or you can raise your hand and I'll unmute you and Rob will be happy to answer your question right away then. We are recording this webinar and we'll be sharing the recording and slides with everyone here via email within the week. It will also be posted on our website at www.shiftshappening.ca. Great. So it is with great pleasure that I introduce Rob Pope, a senior consultant with Ecolighten Energy Solutions. Rob has vast knowledge and experience in the HVAC industry, and he's been involved with installing and servicing energy efficient systems basically since day one. So thanks, Rob, for joining us today and imparting your wealth of knowledge on us, and I will pass it along to you.
Thanks, Jenna. Thanks, everybody, for showing up. We'll just get right into it. Second. There we go. So this morning we're going to talk about mechanical ventilation strategies, HRV and ERV basics, contractor considerations, the technologies available, and code requirements, standards, and the resources and training. Ventilation, I think everybody is probably aware, is about injecting some fresh air into the building to keep it healthy and fresh, among other things. And in that respect, there's two general categories of mechanical ventilation systems. There's a typical unbalanced system, which has been common practice for many, many decades and still very common. And then there's the balanced system, typical balanced system. The unbalanced system relies on two things. And as you can see here, it's fresh air injected into the return air portion of a forced air system. So that's usually a 4-inch pipe or a 5-inch flex coming into the return air duct and gets distributed through the supply ducting throughout the house. And it also has a principal exhaust fan. So the idea is that exhaust fan, which is usually bath fan, is running continuously. So that's getting rid of air, stale air, and being replaced with fresh air this way. The reason it's unbalanced is because it's really impossible to predict the amount of air coming in when reliant on your furnace or your forced air system, your air handler, because that air handler obviously has a very large capacity of airflow. So when that thing is on compared to the bathroom fan, which has a low capacity airflow, it can be positively affecting the house. In other words, a positive pressure, to be more precise. Right? On the other hand, if that furnace is not running in continuous mode, it's off, then what you're relying on is a very passive way of getting air into the building. And that, meanwhile, that principal exhaust fan, which is, for example, your bathroom fan, is still running. So it's taking air out, but the amount of air coming in may be unbalanced, which means you have a negative pressure in the house, which has its issues. Balanced system, on the other hand.
Rob, sorry, could I just ask you to speak up a little bit? There's just some people
okay.
are having a hard time hearing you. Thank you. Sorry to interrupt.
How's that? Is that okay? Yeah, okay.
That's better. Thank you.
Balance system in our context is an HRV or an ERV. And you can see here, the ERV is tied into the forced air system in this example, but it can also be independent. For example, if you have a radiant heated house, radiant floors or baseboards, it's balanced because the same amount of air is coming in as is going out. A little bit more about an unbalanced ventilation system versus a continuous and balanced ventilation system. So traditional practice for ventilation relies on a single exhaust appliance, as I just mentioned, typically a bath fan, running continuously. That's why bathroom fans are rated with a zone rating. It has to be under 1 zone, so it's quiet, because traditionally people were annoyed at their fan running all the time and they shut them off. It has to have a low zone rating, under 1 zone, for that reason, and therefore quiet, so people don't shut it off, and it runs 24/7, always taking air out of the building. At the same time, your 4-inch pipe bringing fresh air into the return air really relies on that furnace running continuously all the time. Because if it isn't, your bath fan is running, your furnace isn't running, and the amount of makeup air coming in is unbalanced. You can't deliver fresh air around that building to each of the rooms as effectively as it could be if it's running. This is not the recommended approach to ventilation anymore, because this year we're going to be doing minimum step 3 throughout the province, which means we're at 2.5 air changes or better. In other words, it's a tight house, right? All new construction, tight house. Even in retrofits, if you're going to do any kind of retrofit to the house, tightening and sealing that house would be one of the potential approaches to improving its thermal efficiency, and therefore, even in retrofit, you're going to try and get to a tight house. In a tight house, you need a mechanical ventilation system that's predictable and balanced. Here's some of the issues that happen with the effects of house that's too positively pressurized or negatively pressurized. I mean, think about it. All the stuff in a positively pressurized building is trying to go out. It's outbound, and that gets into your assemblies. It's going to create excess heat loss, the potential to create mold and mildew and rot in your assemblies if moisture gets into your assemblies and stays there, right? And negative pressure similarly does the same thing, although it's bringing air from outside into your assembly. So whatever's going on outside is trying to get into the house because the house wants to maintain a neutral pressure. So if you create a negative pressure, it forces air in through all the breaches in the envelope. And naturally, the issues that are associated with that are reduced significantly with a balanced system. When a building is high performance, And when I say high performance, it's just meeting current code requirements. So it's reasonably tight. It's going to be 2.5 air changes or less. And it's well insulated. It's probably got good windows and all the kind of things that help make it meet the requirements and compliance requirements of step code 3 at least, or better. In a house like that, you really need to be in control. You need to be in the driver's seat for the ventilation, knowing how much air is coming and going, and ensuring that it's balanced and continuous. Otherwise, in a tight home, you're going to run out of oxygen. A balanced ventilation system using a heat recovery ventilator, HRV, or energy recovery ventilator, ERV, should be considered for all new homes and any retrofits that are intended to build a tight envelope from a leaky envelope, for example. They improve the home's energy efficiency, and they reduce the amount of heat loss and heat gain to some degree. They manage the humidity level in the house, and they keep it fresh. And they do it very quietly and very evenly. Is everybody hearing me okay? Thanks. So what is an HRV? It's simply a box with fans in it and a heat exchanger. And that heat exchanger transfers the incoming air, the fresh air from outside, transfers the heat to it from the outgoing air, the air that's the stale air that's leaving. It does it through a heater core that it doesn't actually mix the air. That's a misconception I hear a lot of times, that the outgoing air and the incoming air are mixed together. Not, they're separated by small film channels in that heater core. Difference between an HRV and an ERV. An ERV does one thing extra that an HRV doesn't do. It recovers the latent moisture in the heat. It takes that, it basically recovers some of the humidity. So in dry climates, which is effectively almost all of BC except for the lower mainland area, coastal areas, it is the better choice. And if you're in a dry climate, especially in the wintertime, the ERV is going to recover some of the humidity that otherwise would be going outside to help prevent it from getting too dry. Types of systems we have, well, we have a standalone system versus an integrated ventilation system. Standalone is it's independently piped. It's not integrated into the forced air system. So it's for houses with radiant heat, for example, or baseboards. In other words, if you don't have a forced air system. And HRV can work very well with in that context, just piped independently. On the other hand, if you have a forced air system, you already have a way of delivering air to all the rooms. You might as well use it. So you tap it into the forced air system, the fresh air side. The fresh air gets tapped in. The exhaust side, typically from your bathrooms, is still independent. And one of the critical performance attributes of any HRV is how efficient it is, right? There's a minimum of 60% efficiency required. That's at 0 degrees. That's measured at 0 degrees outside temperature. It's called the sensible heat recovery efficiency. It is a specification that exists on all HRVs on the market. And it's third-party rated. It goes from, you can get them lower than 60%, but yeah, 60% is the minimum required. But it goes all the way up to 95% efficiency. One of the other considerations is what kind of controls and finishing details. Like anything to do with air, there is quite a variety of grills and registers. The most typical are round diffusers. Usually they're referred to as whisper grills, but with some planning and coordinated design, you can pretty well do anything you want as long as you're doing it in a way that delivers the air you need to the rooms you need them in and exhaust them out of the rooms you need them exhausted out of. So there's quite a variety of ways to finish the ventilation system using an HRV or ERV. One of the other considerations is controls, how to control it. A lot of contractors I talk to, mechanical contractors, prefer to put the controller in the mech room because, as they often put it, they don't want the homeowner messing with it. Personally, I don't think that's an issue. The control that you have over it is pretty simple. On a good controller, you can set the humidity level so it goes on to a higher speed when that humidity level is achieved. Or you can just set it to a continuous low, which is the recommended way to do it. And if you have a party, there's a lot of people over, or you burn some toast, and you want an extra ventilation, and you can, using a controller, kick it up to a high speed. Equipment selection. So there's a few things to think about when you're considering an HRV or an ERV. One of them is airflow capacity. Obviously, the choice will be one that meets the code compliance, right? So that's the first consideration. Does it meet code compliance or not? Another consideration is its efficiency. If it's an ERV, it's measured in total heat recovery efficiency. But this is just taking into account its ability to recover the moisture latent in the airstream. Another consideration is noise level. They'll all have a rating, a decibel rating, and of course there's some louder than others, and so that would be a consideration. Is you obviously, if you want a quiet one, you want to look at that sound level and make your choice, or at least have that impact your choice to some degree. Filtration. Every HRV comes with a standard filtration to protect the heater core, which is more or less filtering out things coming from outside, like bugs and stuff like that. But you can upgrade to different levels. One example is in areas where there are forest fires. You don't want that smoke in the house. Well, your fresh air intake is the way in for that smoke, other than open windows and doors. So you could filter that smoke with a charcoal filter, for example. So this is another consideration with HRVs. As I said, control options. It's not just a functional part of controls. They also come in different aesthetics as well, if you want it. If that's important, you choose your control option based on what it looks like and how it functions. In a lot of cases, people are very content to just leave it on low and forget about it. If the controller is there somewhere in the mechanical room, and if you need to, you know where it is, you go down there and turn it up or off. Cost, obviously, there's quite a range of costs between different products, and market availability. And the reason I say that is because throughout the province, in all the different regions, there's different support for different products. You get contractors in some parts say, I can't get that life breath here. It's 6 months away, or my supplier doesn't carry it. They're a Benmar dealer, or vice versa. So it's also what's available in your region. Obviously here in the Lower Mainland where I am, or somewhere like Victoria, you pretty well have all the choices you want. But it is my experience throughout the province that's not always the case. So market availability is also a consideration. In existing homes, it's a bit of a challenge because you don't have a clean slate to work with. You're kind of stuck with what's there. In most cases, it's you have finished walls and ceilings throughout the building. You have a small mechanical room. How do you get an HRV in there? That's a challenge. It needs room. In a lot of existing homes, the mech room is not really a mech room, it's a closet with a furnace in there, right? In that case, you have to find, a closet that can be used, or storage room if there's one, or somehow make room in the mechanical room. The other issue with existing homes is even if you can find room in the mech room to put the physical HRV and pipe in, you still are not benefiting the house very much if you can't get at least some exhaust from the bathrooms, or at the very least from an area of the house at the top uppermost level, somewhere up there, so that you're not short-circuiting the ventilation. You want it fully distributed, right? So that's another challenge, and there's ways to do that. Going up closets and utility rooms, that kind of stuff. Sometimes you might have to open up a wall or a ceiling to do it. But you really, at the very least, need to find a way to get at least one exhaust point at the highest level of the building. The other thing to consider too, in an existing home, if there's nothing being done to tighten up that envelope, then you have to stop and think, is it worth it, really? If a house is really leaky, and existing homes can be, depending on when they're built, 5, 6, 7, 10 or more air changes per hour. If that's the case, then the HRV is not going to do anything for that house, and there's no point having it. On the other hand, tightening up a house as part of a general retrofit, so maybe windows or insulation and air ceiling drafts and that kind of stuff, is a really good approach to improving the efficiency of the building generally, of course. And in that case, an HRV is an important consideration. Just to reiterate, as homes become tighter for energy efficiency and comfort, a properly designed and installed ventilation system is pretty key. Residential dwelling units, houses, must include mechanical ventilation system to meet Section 932 and or CSA F326. That's in the building code, so it's required. Some of the components of that requirement include a principal ventilation system that provides supply air and includes an exhaust fan, kitchen and bathroom exhaust fans. If the building has a heated crawl, you need components to integrate the ventilation of the crawl with the living space above it. And I'm going to show you here 3 commonly used options to meet those compliance requirements in the code. So this is one that we had been talking about earlier, with fresh air piped into the return air of the forced air system. Again, this is not the recommended approach for new homes because they're tight, and we can't control the pressure in the building and the how fully distributed the air is in the house. Option 2, this is to incorporate an HRV with the forced air system. This is the ideal approach, and this is the one that's going to become the common approach. This is the recommended approach, the forced air system. And finally, we have, there's a lot of homes, mostly in the lower mainland, that have radiant in-floor or baseboard radiators, for example, that don't have forced air. And in that case, you would have a dedicated HRV system. The ducting, or in most cases, it's not actually ducting, it's piping, is independent and distributed throughout the building. This is also a recommended approach. When it comes to design, an HVAC design, including HRV or ERV, is not yet a common practice. It's going to become a common practice. In fact, down the road, it'll be a required practice, right? But right now, it's still not common for Part-9 buildings. For all ventilation designs, the plans and specifications submitted would include, and not limited to the following: a ventilation checklist worksheet, and I'll show you an example of one. And by the way, this ventilation worksheet is pretty common in most jurisdictions throughout the province. It'll include the equipment type with rated efficiencies, and ideally include floor plan showing the routing, the general layout. Where's the pipe going? What's the pipe sizing to meet the distribution requirements of the code? So here on the left, you see the example of ventilation checklist. This is required in a lot of jurisdictions, not all, but in many. And on the right, you see a snapshot. This is a portion of an HRV design. And what it's showing from plan view is, there's the HRV in the Mac room there, and you've got pipe going outside for your fresh air intake and your stale air exhaust, and then you have pipe being distributed throughout the building. So it's showing you where's the pipe going, what's the sizes of the pipe, how it's branching off, and where it's being delivered. When it comes to equipment sizing, the capacity of the equipment has to meet at least the standards in BCBC 93235, and that's based on, there's a table in there, and it functions with the square footage of the building and how many bedrooms, and that's how you choose. You're basically going this much square footage, this many bedrooms, and that is the ventilation required for the building. That's 932. CSFA F326 is more room by room. It determines how many CFM you need in each room, exhausted and delivered. It doesn't go by square footage in the amount of bedrooms. So now if you've done that, now you got your equipment size. Remember, that's a minimum. You can go bigger than that. The next criteria is that it has to be at least 60% efficient at 0 degrees. Most equipment in the market is there. I mean, there's stuff you can get Home Depots and places like that that doesn't have those kinds of ratings, and maybe they're okay if you want to ventilate, your workshop or something like that, right? But in new construction and retrofits, you need to meet that 60% efficiency. So that's your next criteria after the capacity, and then finally it's the layout. Ideally, an HRV system that's integrated, for example, with a forced air system, is exhausting from all your bathrooms, maybe even your kitchen. Basically, the points where stale air or humid air is generated, that's what you want to get that out of the house and the fresh air in. If it's a forced air system, obviously it's going to be delivered to all the rooms anyways as a portion of the total volume of air in the building. If that can't be done, at the very least, and the code requires it, it has to be one exhaust point at the uppermost level of the building at 2 meters above the floor. If you do that, you meet the code requirement. That's not good practice. But if in a pinch, if that's all you can do, then that'll at least meet the code requirement. So like most critical components of a good HVAC system, it's not wise to simply turn it on and call it a day. And I put that in there because it is my experience and the experience of many others. That is mostly what happens. Right? Balancing that HRV is critical, really, really important. You need the outgoing air and incoming air to be the same. You need to measure it. There's methods to do that. There's all kinds of established checklists and report documents that you're supposed to put that onto. Independent grills dedicated to the system must be adjusted to match the design flow rate for the room it's serving. Okay, so just imagine you've got your mechanical room in the basement. Next to it is a small powder room. And then on 2 stories up in the opposite end of the house is a master bedroom with a master ensuite. Now, obviously, those 2 rooms need different airflow, right? And one is right close to the machine. So if you just let it go, what's going to happen is that small powder room is going to get way more airflow than it needs compared to the master ensuite, the opposite end of the house, right? So it's really critical to go to each of the rooms and balance the flow appropriate for the room it's in. And finally, if you've done all that, it's important to make sure it's recorded and left in a report that future technicians can come and see that it was done. You know, and not just future technicians, but also anybody inspecting it, you know, authorities with jurisdiction or the designer. Like when I design a system, I expect the balancing to be done. And if I arrive on the site and I know it's been done, but there's no report, then I have to say, no, it's not been done. If you do it, leave a report. And if there's no report, then it's effectively not done. Here's a couple examples of reports. These are easy to get, by the way. On the left here, you see an example of an HRAI balancing report. On the right, the City of Vancouver commissioning and balance report. These are just a couple examples. If you fill this in, that means you're checking all the boxes. You're going through the process, the whole process of balancing and commissioning the system, and it's recorded. Some of the technologies, well, we've got what we call specialized equipment, the Zender ComfoAir, for example. That's a product. It is almost exclusively for passive homes. In passive construction, it's the only one that's certified by Passive House that you can get here in Canada. It goes to 95% efficiency. You can use it in any home, but it's an expensive piece of equipment. So there's other options for non-passive homes. Lunos through the wall. This is good for small cabins, lane houses, suites. It's a through the wall. It's not a fully distributed system. So you have to be careful because remember the code requires that you deliver air into all the living spaces. If you have a through the wall system that's not ducted or fully distributed, this can only deliver fresh air into the room where that wall is that it came through, right? And if they're down a hall, there's a bedroom or something, then you'll need another one in there. So you got to be cautious with the Lunos through the wall, but they're not expensive. So putting a couple in, it's not that big of a deal, and it may be more cost effective and make more sense than a fully distributed standard system like the ones we have below, the Life Breath, Venmar, Fantech. Those are very common systems, the most common. But just to provide a little heads up, this is a note on efficiencies. And I put this in there because I don't want anybody to spend too much time worrying about the efficiency of one HRV over another. It's really not that consequential. So here's a house. This is an actual home in Roslyn that we worked on recently, step 3, 2,500 square feet. And here's a load calculations done with F280. And you can see outlined in red there, the heating load for an HRV with 65% efficiency, which is what actually has gone into this house. So 31,321 BTUs. It's just under 10 kilowatts. With the 95% ERV, if we were to put one of those in there, how much heat loss do we save? Not much. You can see here, we still have a heat loss of 30,054. It went down. It went down for sure. It went down, but not by enough to justify something like a Zender, which would be 3 times the cost. If the product that you originally specified is not available, don't sweat it. If the efficiencies are not as good, it's not that consequential. Code requirements in National Building Code, in BC Building Code, in fact, the Vancouver Building Bylaw are all matching. Section 932 requires a balanced, fully distributed ventilation system for all new construction. It also points to CSAF 326 as an alternate path. This is in Ontario, is the most common way of doing ventilation, F326. In BC, not so much, except in passive houses, for example, you will use F326 more than you would 932. Training. There is a few places available, TECA and HRVI, too, I guess, not a few. TECA has a couple of different courses, ventilation guidelines, which is general, and heat recovery ventilator and design installation. That was developed for the city of Vancouver, but it's applicable to anywhere outside of the city, of course. It teaches you how to design the system. And the reason that is because the city of Vancouver did their own studies and they found such a failure rate of the way HRVs were installed that they decided they had to support creating a certification in a course to equip installers with knowledge of how to design these things properly and provide Vancouver with a way to verify these installations. HRAI is more Ontario focused, but it's national. And their courses have been around just like TECA for quite a long time and is equally as effective as TECA for getting a certification and learning how to design and install a ventilation system. Here we have some, I guess this deck will be available to everybody. Is that right, Jenna? Because we have some links here to other resources.
Yep, yeah, that's right. We'll send these slides out to everyone via email.
And that's it.
Okay, great. Thanks, Rob. We've had a few questions pop up in the chat. So why don't we dive right in? I'll just go through the questions in order, and then if any other questions come up, feel free to add them to the chat or raise your hand and we can answer them as they come up. So Bruce Murdoch, he asked if there's an HRV available that will sense the building out of pressure balance, like when a range hood is exhausting and capable of rebalancing it, or are they all equal air in and out?
You can get a third-party device to put into your HRV. You can do that with the Zender product because you can modulate the flow, or any HRV that you can modulate the flow, but they don't come inherently with the HRVs, but they are available as a third-party sensor.
Great.
I have to say though, it's not a good way to go, right? The range of an HRV is finite, and you don't want to, if you got a range exhaust somewhere that has a lot of capacity, for a sensor to be saying, okay, I've got a negative pressure happening here potentially, just bring in the fresh air and slow down the exhaust air, right? What you're doing is generally affecting the pressure in the building, but you're not precisely doing it. There's better ways to do that. If you have a, say you have a tight home, very tight home, and you do, like to cook and spicy stuff, and you want the exhaust outside, and you want a high capacity exhaust. First of all, the high capacity exhaust, you have to be very careful about, because the house only has so much volume to exhaust. But if you really want it, you can get a passive makeup air, for example. It's interlocked with your range. That's a lot more precise. You put a pressure differential switch in there. It's actually measuring the airflow going out, right? And it'll only bring on the passive makeup air when it gets to the exhaust, high speed, for example. You don't want makeup air coming on low speed or medium speed, for example. You only want it when you need it. So that's a better way to do it.
Great. Thank you, Bruce. I hope that answered your question. If not, let us know. And then our next question, Jason Cameron asked, how do wood stoves affect balancing of these units?
It's actually not affecting the balancing of the unit at all, but it's in fact, it's impacting the house. If you have a wood stove, it's going to want oxygen to burn, right? So ideally, you have a wood stove that you're piping in that oxygen. It's called combustion air, like a 4-inch pipe directly into the burner compartment of the wood stove, so it's not using house air. That's ideal. And you have to be careful. The wood stove generally has a gasketed door that is tight, right? But it's not technically airtight. And if you have an exhaust appliance, like if you get a tight, like that 2,500 square foot house, for example, if they had, say, a 300 CFM exhaust fan in there, the house can only handle so much air. It doesn't have 300 CFM to give it, after a short period of time, and it'll create a negative pressure. Now, if you happen to have that wood stove going at the same time, potentially you'll draw whatever should be going out the chimney into the building. So if it's a wood stove, it's going to create potential smoke damage. You'll at least see it, right? If it's a gas appliance that's open combustion, then it's a whole different story, because you won't know. The products of combustion like monoxide, aldehydes, all those nasty things will come into the building. You won't even realize it. And so that's a serious life safety issue. With a wood stove, it's still potentially a life safety issue. Technically, it's considered naturally aspirating fuel-fired appliance. And if you exceed a half air change, you have to have makeup air according to code. So that's how it affects the house. Meanwhile, the HRVs over there doing what it does. It's independent of all that other stuff that's going on. So it doesn't affect the balancing in the HRV, but it does affect the potential balance of ventilation in the building.
Okay, great. Thank you. And then Tony Bartco just commented, fire blocking for the Zender is a nightmare. I don't know if you have any response to that.
Fire blocking?
Mm-hmm.
Oh yeah, because they're a home run system using plastic pipe. Yeah, got to take this with the understanding that I have a bit of a bias probably. The Zender is a very, 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 very good product. There's no doubt about that, but it is very expensive. It's 3 times the cost of a standard HRV. And Passive House Institute, says that you got to have this, and or something that they have certified, which the designer is going to do again. It does a great job. It's a wonderful product, but it is so expensive. And in my view, any HRV that's over 60% efficiency will do the same job. So I'm a bit down on Cinder for that reason.
Okay, great. And then Anna asked, please, could you explain again what the issues are with the little lunos? I thought they were designed to be able to work alone for small spaces or rooms.
Yeah, that you don't duct the lunos, right? So imagine if you got a cabin, a lane house, a suite. It's perfect if you've got, like a studio, there's your living room, kitchen, bedroom, all in one open area. Now you're meeting code, you're delivering fresh air to the open area like the code requires. And you're, taking stale air out. It's an in and out. But if you've got other rooms down the hallway, you're not actually delivering fresh air into those other rooms, which is required. So that means you need another luminance. Obviously, logically, once you get past a certain point, like if you've got about 3 or 4 of these things into a lane house or suite, then it doesn't make sense. Then a regular HRV is a better option. But if it's 1 or 2, from a cost point of view, it's more cost beneficial, as long as you're meeting code. But it's not, if you're not meeting code, you really need to upgrade to a fully distributed HRV, like the Life Breath or the Fantech or the Venmar, one of those.
Great. And Anna says, gotcha, thanks. So nailed that. All right. And then we had, sorry, I just lost myself in this. Tony asked, can you use passive ventilation for a secondary suite in a step 3 house?
Yeah, it's kind of awkward. You're technically, that is a compliance path. You're allowed to do that if it's under 1,000 square feet in 1 story. Passive ventilation. What's passive ventilation? You still have your exhaust fan, your bathroom fan, for example, dedicated, and you call that your principal exhaust fan. And now you got to bring air in, and you still got to do it into each of the rooms. So if you've got 2 bedrooms and a living room, there's 3 points of entry of fresh air, and that is, as it suggests, passive. It's just, there's no fans, nothing. You got to pipe it from outside into the rooms. Okay, so that's fine. It's not, very inexpensive, and it does the trick. It ventilates it. But problem is when you do your blower door test, you've got, in that example, 3 holes, right? And that's when it becomes a kind of a catch, right? You still need for step 3 to meet the 2.5 air change, right? And if you've got 3 holes in the house, that might not be possible. So that's the paradox with the passive ventilation for smaller suites and greenhouses and stuff.
Great. And then Tammy has a question. Thanks, Tammy. I had the same question. What is the ideal threshold for ACH, so air change per hour, before you'd suggest it's worth it to install an HRV or ERV? So I guess in retrofit specific situations.
That's a good question. There is no sort of scientific threshold that's been measured, calculated, and exists in any kind of standard. There has been many agencies, or at least a few that I know, that have suggested 5.5 air changes. I think that might be a little disingenuous, because there's a lot of new houses that haven't had to meet step code 3, for example, or any step code, that are 5.5, right? And I would still recommend an HRV in those houses. So I think it's higher than that. But in reality, most existing homes are, they're really leaky, right? So personally, I think if you're at 7 or over, that's when you would say, yeah, there's no point. HRV makes no sense. Between 5.5 and 7, it's gray. Then it depends on budget and how practical it is to put in a whole bunch of other considerations. I mean, ideally, you have an HRV in a house that has 5.5, for example. That'd be nice, right? But I wouldn't think of it as the end of the world if you didn't have an HRV in 5.5 air changes. Anything under that, you really do need an HRV. So as you can see, it's a bit of a gray area there.
Great, thank you. Our next question is from Bruce McNeil. Is a gas range considered an NAFFVA?
No, it's not.
Okay. Jacob Nichols asked, typically we have been installing HRVs. We have been told by industry partners to install ERVs. What are your thoughts?
I would default to an ERV everywhere outside of the coastal region. Any cold area of Canada, which is almost all of Canada with some exceptions, an ERV is a better way to go. But if you can't get on, if for some reason, and this happens a lot, I get a call from a contractor, the ERV is not available here. We can't get it for 6 months. I need something now. Can I put in the HRV? Sure. It's not a huge difference. It's a difference that's worth defaulting to the ERV instead of the HRV everywhere except the lower mainland Vancouver Island. But I wouldn't worry about it if you can't get an ERV and you use an HRV instead. It's not that big of a difference.
Great. Joseph Hughes asked that you mentioned training available specific to installation for simple homes. Do you know of any online resources? Joseph, maybe we'll follow up with that. If we do find some available resources, I'll make sure to include them in the follow-up email, because we do have a couple more questions to get to here, and then I wanted to save some time just to pull some feedback. So Sola asked, can conducted single room HRVs be used to meet the code for tiny houses? I work for a single room HRV manufacturer and we get this question a lot. And then Joe, I see your hand up there. We'll go to your question afterwards.
That can work. The basic fundamentals that have to be met are, is it HVAC rated? Is it third party rated at 60% efficiency or better? Because that is a compliance requirement. Can you deliver the fresh air into each of the living spaces, bedrooms, living rooms, so on? That is a compliance requirement. Can you exhaust from that, if it's more than one level, the highest level at 2 meters above the floor? Because that is a compliance requirement. So those three are met yet, then you can.
Great. And Joe, I'm just going to give you permission there to unmute. You can ask your question. Go ahead.
Hey, Rob, how you doing?
Hey, Joe.
Good. Hey, so a conversation with you a few years ago about ERVs. We switched over and started using them, but we started to have a real problem with getting rid of the initial moisture in the house that first winter. And I'm just wondering, is it the equipment set up wrong? Is there an issue with the balancing, or do you think that there's some other way to deal with that? We've had to bring in like a commercial dehumidifier to get rid of the moisture in some of the houses because there's just so much, and the ERV won't allow it to use.
Yeah, and in those situations, now obviously there's a lot of different things could be going on, right? So what I'm going to tell you is probably more about what's typically going on, but not precisely. in any given situation. But one thing is houses built in the different seasons will accumulate a lot of moisture that is initially there when you first get occupancy. Not all cases, but in a lot of cases. And so there's an excessive amount of moisture in a new home in a lot of cases. The other is the balancing of the system. If it's not balanced, you're not going to get the kind of ventilation you need. This is very common with unbalanced systems as well. The other thing is to see, okay, what's the source of the moisture? Where's the moisture actually coming from? Is it just normal occupancy? Are they kicking up the unit at high speed when they're using the bathroom, for example, having a shower? Are they using a range exhaust when you're cooking something like boiling pasta or whatever? It's really important to understand the occupancy usage. You know, what's going on, when is it happening, and what are you doing when it's happening? Is there a fan on or not, you know? So that's another consideration. It's a bit of a forensic kind of audit you got to do in a lot of cases, because the occupant has such an influence of how they live and how they understand the system. Has a large influence. And in some cases, it is just the system is not sized appropriately or not distributed appropriately. Like it's not, if you mess up on the sizing of the equipment in the first place, that'll be a problem. If you mess up, you get the sizing right, but you mess up on the piping and the ducting, that will be a problem. So as you can see, Joe, it could be any number of things. But generally speaking, keep in mind this: if you're in Quesnel, right, or if you're in Vanderhoof, I was just there not too long ago looking at the project. If you're in Kootenays, in all of these places, even Whistler, one thing is for sure, it's a cold, dry winter, right? And the issue of excessive moisture means there's something else going on. It's not about the climate. It's a cold, dry winter. Typically, the humidity levels get really low, right? At winter time when you get those kinds of climate conditions. So it's something about either the system or the use in the house that's happening, that's causing the issue.
Okay, no, that's not, I was just hoping that, we're just trying to figure out whether to get rid of the ERVs and go back to HRVs, but it sounds like we just need to pay more attention to how our mechanical guy is doing the install and what they're doing.
Yeah, it's not about whether it's an ERV or HRV, right?
Okay.
The climate is, you know, I mean, the evidence is too overwhelming about that. It's about how it's installed.
Yeah.
And then, you know, in some cases, occupants don't get the handover that they really need, you know. They don't know certain things, right? And so they're, if you're not able to kick that unit onto high speed when you have a shower, you know, for a little while, if it's stuck on low speed, then you're not going to get an effective evacuation of that humidity. And that humidity will move throughout the building, right? And, you know, in some cases, it'll end up condensing on windows and other things.
Mm-hmm.
Okay, great. I'm just, sorry, thanks for your question, Joe. I'm just looking at the time. We're about a minute away from 9 right now. So a big thank you to Rob.